I'm presenting, this is part of my PhD work in parallel compilation for stream processing. And hopefully I have a decent mix of practical and academic concerns here. So SKIR is an acronym that stands for the Stream and Kernel Intermediate Representation. It's basically LLVM plus intrinsics for identifying and manipulating streams and kernels, and graphs to streaming computation composed of those things. We also have language front ends for streaming languages, code optimizations to target our dynamic scheduler. We use the LLVM JIT backend for CPU compilation, and we can also target GPUs using OpenCL. So first of all, what is streaming compilation, or what I call stream parallelism? So this is any algorithm that can be expressed as independent stages of processing on regular flows of data. So this could be a lot of things. At the most fine-grained level, it's something like DSP processing. And in our research lab, this is what really motivates this work in the area of software-defined radio, cognitive radio, and that kind of thing. But the same programming model applies to all sorts of problems. At the most coarse-grained level, you have like network processing and like Twitter firehose processing, or things like that. So this graph on the right, which I lifted from some slides out of MIT's StreamIt project, basically shows how this programming model can be used to express three different forms of parallelism. Pipeline parallelism on the vertical axis, sort of task parallelism among things in the horizontal direction, and then in the second kernel here. And so these boxes represent processing kernels, and the arrows represent data flows between them. And then this represents the fact that you might have data parallel kernels embedded in this graph. And so these are things like your OpenCL kernels, or other things you might want to vectorize or run on a GPU. Oh, what happened there? Sorry about that. Technical difficulties. Okay, there we go. Sorry. Really? Okay, thank you, Ubuntu. Okay, so formally, what do we mean by stream processing? There's basically two formal models that are used to describe this model. One is a Kahn process network. So this is the more general form, where you have a network of processes communicating over first in, first out data channels. And really, the only restriction on the kernels within that graph are that they're deterministic, so that any interleaving of execution of the kernels in the graph produce the same output. And so the network is deterministic, but we can't really prove other properties about it, like whether or not it deadlocks, or whether we can schedule it with bounded buffer sizes, that sort of thing. A more useful restriction of this model is synchronous data flow networks, where each kernel is restricted to have fixed input and output rates. So this really lets the compiler reason about the overall graph. So you can slice it and dice it. You can merge kernels together, depending on your goals. And it allows proving that something is deadlock free, and it allows static scheduling techniques because you can for example, prove or more correctly, figure out the buffer sizes necessary between things. So why do I care about stream parallelism? Well, as we all know, in addition to becoming more parallel, hardware is becoming increasingly diverse. So 4 of these are x86 nominally, and they're very different architectures. One compiled parallel program might not execute optimally on all 4 of these x86 architectures. They have very different characteristics. The Sandy Bridge has an integrated graphics processor with shared L3 cache, where Knight's Corner has 50 plus x86 somethings in it. So you know, and even in LLVM, despite the limits of portability in the bytecode, you could pretty much generate one bitcode program that can target all these things. But if you're trying to optimize for the characteristics of the parallel hardware, you're not going to be generating very portable code. Oops. That was the mistake I made last time. Okay. So, as I mentioned before, this applies to lots of things. Media processing is a big one. Any kind of compression, decompression, but also physics things. Any data parallel computations you might use a GPU for. And as I mentioned before, our motivation is signal processing and software radio. So another reason why I think this is useful is because I believe in general that embedded domain-specific programming models for parallelism are a useful thing. So here you basically embed some domain-specific knowledge into your language, compiler, or runtime system. And because of that, you have both higher productivity because you have an abstraction tailored to your program, to your problem, and you also might get better performance because the compiler can infer things about your program that it might not be able to if you were using, for example, just locks and threads, right? Like I like to say, it's your favorite language with better parallelism. And there's plenty of examples of this out there. This is just another one. So the runtime organization is that you pass your program through a standard compiler, but then at runtime, you have your domain-specific compiler that does something useful to target the parallel hardware you're interested in. And so on the left, this is the same model in the SKIR system. SKIR is organized as a JIT compiler for performance portability, so being able to target a variety of parallel platforms with one compiled bit code or executable. And then this also allows you to have sort of dynamic program graphs that you wouldn't be able to have in a static model. So you might have scheduling policies, for example, that differ with respect to throughput or latency, and you might want to modify that graph to give a different assignment of resources to a certain kernel at runtime to affect those policies. And then, of course, since we're in a JIT environment, we can do this dynamically and apply dynamic optimization. So we do this by extending LLVM with a set of intrinsics. These are the intrinsics down here. And if you can read this on the left, this is an example program. I'm going to step through this. This is pseudocode, not LLVM code, just for readability reasons. But so we're going to construct and execute a 4-stage pipeline. So first thing we do is execute this SKIR stream intrinsics. So these just allocate an edge in our stream graph for our algorithm. But in the runtime system, they're instantiating real buffers. We do the same thing for the kernels we're interested in. So these are just the nodes in our graph, and these are this says SKIR kernel, and this is just a pointer to these procedures up here, which are our kernel work functions. And then we're also passing in, we can also pass in data. So then we execute a call instruction, intrinsic on these kernels. And then as we execute call instructions, these things are spawned and start running. At the end, we wait for the last guy to finish. If this guy stops producing data, that will propagate through the graph, and the whole thing can shut down and garbage collect or whatever. So this is a simple example, and obviously a little contrived with very small amounts of work, but pipelining, for example, applies to a lot of real problems. So the easiest way to get at these intrinsics is we provided a one-to-one mapping of SKIR operations to C intrinsics. So it's pretty straightforward. Here's a kernel that just pops two things off an input stream, subtracts them, and pushes it to the output. And then on top of this, we can build bigger abstractions. So this is an example of a C++ library that maps object-oriented stream parallelism onto our SKIR intrinsics. So this is an n-body simulation from the CUDA SDK. So embedded down in this application, there's a display loop because it's an OpenCL application. Each iteration of the display loop updates the state of the simulation, which runs this three-stage pipeline to completion. I've blown up the middle stage of the pipeline, which does most of the work in this example. And so basically what it's doing is it's going through the n-squared simulation state, updating all of the particles in the system, and then the final stage here just updates that to memory. So this is one way you can get stream parallelism out of sort of a data parallel thing, is that this top kernel is basically just emitting the iteration space of a loop, and this is a subset of that iteration space, and then this collects it all. And so in this example, we're actually running the middle kernel on a GPU and getting pretty good results. We also have a front end for the StreamIt language. It's a research language out of MIT, which allows you to statically describe stream graphs. And this is in the synchronous Dataflow model. So pretty standard compiler flow for this one. We have our front-end compiler, emits our SKIR bitcode, and we JIT and schedule that at runtime. And finally, we have a JavaScript front end, which basically demonstrates the use of this as an embedded domain-specific language, where we have StreamIt-style program construction, like in that previous slide, but then the stream parallel model restricts the program enough that we can run type inference on the JavaScript, get native code out the back end, and then offload that to the SKIR runtime. So our runtime has a RPC interface supporting shared memory streams and shared memory state. So that has really good results just because JavaScript is so slow. And then this is in an extension to V8 and Node. So how do we compile this? So these are the basic things we do that I'm going to talk about in this presentation. We do analysis, we do a batching transformation. We abstract our kernels as coroutines, but then have a path to get rid of those. We specialize the stream communication to the hardware we're running on. Or, for example, we wanted to do streams over sockets or something, we can do that too. But for shared memory multi-core, this is where we get a lot of our performance. And then we can do graph-wide transformations, where we either fuse kernels across processing cores or or fuse kernels together to eliminate over-parallelization in the graph. And then, of course, we can file for GPU hardware. So our basic kernel analysis just tries to extract static data flow semantics from arbitrary kernels. So recall that we're operating in a Kahn data flow model where a lot of the optimizations in the synchronous data flow model are not available to us. But if we can identify parts of that stream graph that are static, that is, they have fixed input and output rates, then we can do more interesting things. And we also try to identify at this point whether or not kernels are data parallel, suitable for acceleration on GPU. We could also pass this information down from a high-level language as programmer annotations or something for languages that support that, but we don't do that yet. So this just leverages a bunch of existing analysis in LLVM, which made it fairly easy. So before moving on, I have to talk a little bit about our scheduling strategy for these guys. Our strategy is to basically pick a kernel to run and then run it until we either run out of output buffer space or run out of input data. And this is the single-threaded case. So when that happens, we locate the kernel causing the block and just go run that kernel. So this is demand-driven execution. We're following demand for data. The advantage of this is that it's a decentralized algorithm. There's no access to global state or anything like that. And in the case of executing a consumer and then following the demand down to the, executing a producer and then following demand down to the consumer, we actually keep everything in the cache. So that's fairly fast. The only caveat is that we have to avoid just running something with no inputs and just filling outputs unnecessarily, but we do that by allocating fixed size buffers. These are, in the implementation, these are concurrent lock-free queues. So as I mentioned before, we create demand-driven execution by transforming kernels at code generation time into coroutines. So the general problem we have is that for a kernel that has something like this in it, we don't know. So say this is a network processing algorithm, and we're popping a pointer to a stream, a packet off of a device. We're looking at maybe some kind of type of the packet or something, and then we're forwarding it to an output stream or something. We don't know if we're ever going to block on a particular output stream because we don't know when we're going to push to that. So instead of trying to make that decision statically for arbitrary kernels, we use this coroutine style of execution. So we just yield at the point of blocking back to the scheduler. So we can extend this pretty easily to parallel execution. We layer this on top of thread building blocks, but you could use any model really. And the difference is that instead of just blindly switching to a kernel when we make a scheduling decision, we instead try to either do a task steal on that kernel's task or spawn it if it's not executing already. And then, of course, the one that was running is then pushed to a queue and is eligible for being stolen by another processor. So this gives us load balancing, low overheads, context switching, and stuff like that. So as I mentioned before, a lot of our applications that we're interested in are like DSP kernels. So this work in here might only be a few hundred or a few thousand cycles, and having that coroutine logic in that inner loop really, you can imagine, messes with, we don't want to make a loop through the scheduler each time we execute this guy. So, so the first basic transformation we can do is to just wrap a while loop around the body of the work function. And we can do that pretty blindly because these are yielding stream operations, right? So taking that a step further, well, maybe we have a kernel with fixed input and output rates, and we can be a little bit smarter about what we do. Again, if you consider that this might be a small amount of actual work here, you don't really want this construct in this inner loop. It's gonna, because this turns into an intrinsic that can basically touch any memory, can alias with anything, because it's going off and hitting the scheduler, which can then do anything it wants. It can rejit the code even. So this messes with optimization big time. So if we know that a kernel has fixed input and output rates, we just essentially hoist this out of that loop and into just a piece of code that generates, each time we enter that body, how many times that's going to execute. And then we execute it that many times. So practically, this is kind of the impact of that at the x86 level. What happens? This is a little StreamIt kernel that just pops two things off its input, adds them, and pushes them. And it generates all this code if you're trying to do it with coroutines. These blue sections are those while loops. And the oranges and yellows are the actual reading of data off the input streams. The red is the actual work, the add. And so overhead's huge here. On the other hand, when we do it the smart way, this code's pretty good, other than the fact that we don't do vectorization. There's not a lot of redundancy we could get rid of here. So moving to a higher level, another way to remove overhead in that stream graph is to perform kernel fusion. So actually reducing the parallelism in the graph, because typically we might have a program that's over decomposed into tens or hundreds of little kernels, and we might have 4, 8, 12 cores or something like that. So this will reduce both scheduling overhead as well as communication overhead. So the fact that we have intrinsics in here that the compiler can recognize makes it fairly easy to kind of paste these things together and then replace that stream communication with, in this case, reads to the stack or even registers. So this is pretty straightforward transformation. We just compute the input and output streams. We do a renumbering on the streams, basically forcefully inline those things into a bigger kernel, and then relook up the renumbered streams and replace them with loads and stores and allocate instructions. So pretty cool. We've experimented doing this dynamically, and we can get decent speed up out of that. On the flip side, if you have a very coarse-grained decomposition of your problem, you might have like a 5-stage pipeline or something that's dominated by one or two of the stages that happen to be data parallel. So you can do the opposite transformation, which is to just split the thing into multiple parts. So the programming model makes this very easy. We basically just generate the new kernels and do scatter and gathers on the inputs and outputs to exploit that data parallelism. Of course, that's not the only way to exploit data parallelism, but it turns out in practice that this is fairly low overhead. The other thing we can do, obviously, is we can use a data parallel accelerator like a GPU. So this is so in this system, we do that by emitting OpenCL code dynamically at runtime. And the OpenCL backend is just a modified version of the LLVM backend. And the OpenCL API calls are embedded into our runtime system. So since we're in sort of a JIT environment, we can just, here's a 3-stage pipeline where we've replaced one of our kernels with an OpenCL kernel. We just dynamically replace that in the stream graph with a kernel that does the buffering into OpenCL buffers, copies state over, gets the results back, and reads and writes the state to the neighbors. Now we can do this basically for any kernel where we can figure out what the state is, right? So part of the work function parameter is like a this pointer. And if that pointer is typed and it's flat, like it doesn't have random pointers going off, then we can easily compute what that is, shove it in the struct, and ship it off to OpenCL. Our execution strategy is fairly simple at this point. We just run one instance of the kernel work function for every point basically in the iteration space of the kernel. And so in this example, we have a kernel that reads 2 things from its input, does some work, and then writes 3 things to its output. We just dynamically look at how many things are in our buffer when it's our turn to run, and then generate the iteration space, or the work groups, or whatever it's called in OpenCL, to do that. And so this gets okay results. There's still some work that could be done, for example, like loading the data into OpenCL local memory, doing some better vectorization, and things like that. So we're probably 2x behind hand code for that. But it works pretty well. And really, it's a result of 2 things. It's a result of using LLVM as a analyzable representation, and the fact that our programming model gives us well-defined inputs, outputs, and state. It's basically the same thing that allowed us to run type inference on JavaScript code and offload it to SKIR. In this case, we're just offloading SKIR code to OpenCL. So in summary, we're doing optimized stream parallelism using LLVM. So fine-grained parallelism, which we're able to execute efficiently because it's in a form analyzable by LLVM. We get as good as or better performance than existing systems that are out there, at least open source and research systems. And we hope to get it out there as open source soon. We're proposing to use this for ongoing work in software-defined radio and in network processing. We really need to get vectorization in there because that'll give us, 4x right away for some problems, and better GPU cogen. So, thanks. Any questions? Yes, so I was hoping someone would pick that up. There was, so I mentioned the StreamIt project from MIT. So that was sort of an inspiration for part of this work, was that, wow, these guys are getting really good results. They can do FPGA, they can do GPU, they can do all these things, but it's not a useful language. So hopefully putting into LLVM makes it a useful language. But one of the guys in that group did a functional streaming language called WaveScript, where this is for sensor networks. So really the model of computation was just to express computation executing between sensor nodes. But their experiment, bizarrely, was like a location of marmot location based on audio processing in the Rocky Mountains. So yeah. So yeah, mountaineering field work for computer science. Yeah. Huh? Oh, I don't know. Yeah.
So for the scheduling, maybe I'm a little confused, but do you actually do the graph traversals during runtime, or is it just lists that you're going down as far as what's available next to schedule or pass?
Right. So to sort of bootstrap the thing, so for the single-threaded case, Well, the answer is yes and no. So to get the thing running, yeah, there's a single work queue. But as soon as you start executing, then you go into this demand-driven mode where you're really following the edges that you suspect have work to do in the graph. And the same thing happens in the parallel case, where except now you're initially walking a work queue as tasks come in, firing off n, where n is like your number of cores, and then letting it go. Rarely does it actually fail and get back into that loop. For that to happen, every worker basically has to like fail stealing a task, so like somehow. And the only way that can happen is, for example, if someone else stole the task first, right? So, yeah.
You talked about node vision. Is that right now just floating a couple copies of the same node and doing concurrency based on basically all reading off the same depot?
Yeah.
So it's not taking the task and splitting it apart into separate.
It's creating multiple instances of the same task.
Just running.
And running them on different portions. You can think of it as running on different portions of the input and output streams. Yeah. Now you could, if you're doing like automatic software pipelining, or if you're doing some kind of automatic transformation from like a loop nest or something, you could then maybe think about breaking kernels apart like vertically or something like that. But we haven't looked into that.